but we've already done the announcement. I think you've heard them before. We'll go from current slide. By the way, this package that I'm using is called Screencast-O-Matic. It records everything I say as picked up by my microphone and my computer, and everything that's projected on the board in sync. And did you look at any of the videos?
Yes, I did.
That's where they came from. So that's what I just started this time. And let's go from current slide here. And let me also tell you some other things, and I think you probably already sounded like you're doing these. On Blackboard, have you been to Blackboard? And that's how you got the syllabus is there, my locator card is there, the research paper instructions there. So in the YouTube videos, you can hear me talk about all of those, okay? Also, the PowerPoints are there in static form, but if you watch YouTube videos, you see the PowerPoints in dynamic form. I'll talk about them right on the screen, that kind of stuff. It does get picked up because I have an ionizing pen, and that I write on the screen here, it projects it here, so that's recorded too. Okay, there are a few other things out there. Oh, your WebAssign class key. If you're using that, I'm not going to make any assignments on it, but if you want to use them, they're out there. Additional practice, additional there's tutoring help that you can get through that. So there's another way that you can get more information and help there. Then I also put a few websites out there, web links, that either other students have said they found useful or I found and thought they might be useful. Okay. So anyway, all that's there on Blackboard, but the key one to catch up and stuff like that is the YouTube videos. Okay. Now, we're right now in Chapter 4, which is trigonometry, 4.3, which is right triangle trig. And we're just on example 2. We did example 1 last time. So we're going to start with that. And let me remind you that we're going to do 4.3 and then move on to 4.4. Now, 4.3 is a fairly long section. We may or may not finish it today. But when we finish 4.4, then that'll be time for the first test. And your tests are take-home tests. So I'll be giving that to you. Probably give it to you on Thursday, whether we finish 4.4 or not, just so you can get started on it. And unfortunately, when you see the length of it, you'll realize it'd be nice to get started on it. We won't get to, I doubt if we'll get to the part that we've got. But before we get started on example 2, I happened to notice, and I've taught this several times, I'm not sure I've ever noticed this before. There's a little historical note here on page 278 about Georg Joachim Rheticus, I think is how you pronounce his name, way back there, 1500s, 1514 to 1576. So he lived about 62 years, which was probably pretty long in those days. He was the leading Teutonic mathematical astronomer of the 16th century. What does that mean to you, Teutonic? Maybe nothing. It means to me, or my connotation of it is Germanic. So Northern Europe. That would include Germany, but also probably, they probably were different countries back then, so it doesn't even give that, just Teutonic. So it could have been Scandinavia, it could have been, Netherlands, it could have been any of those areas up there, okay? You don't read much about them. You usually read about the Greeks and those others, but the Maoris here. Now, why do I say anything? Well, he's a potential paper topic, or what he found out, other things. The interesting thing to me was he was the first to define trigonometric functions as ratios of the sides of a right triangle. I didn't know he was the first one to do that, so that's pretty interesting too. All right, and it's Nikhil, right? Okay. All right. Okay. So, where we left off last time, we did example 1 on page 278. Getting ready to start example 2. Before we do, any questions? Anything we've done so far? Anything you watched and had questions about? All right. Example 2, it says evaluating trigonometric functions of 45 degrees. So it says find the values. Let me get my pen set up. Find the values of sine of 45 degrees, cosine of 45 degrees, and tangent of 45 degrees. Now, if you were around in the previous section when we did unit circle, you probably know these. Let's not think in terms of unit circle. Let's think in terms of right triangle. So that's what this section is dealing with. Now, 45 degrees. Is there anything special about that? I don't draw very good triangles or lines anyway. Anything special about 45 degrees? Say that again. Right. Uh-huh. And since this is a right triangle, that's going to be 90 right there. Yes, okay, perfect. If this angle is 45 degrees, this angle is also 45 degrees. Excellent geometrical observation there. Now, if those two angles are equal, what does that say about these two sides? They're equal as well, because the same size angle with a right triangle, yeah, that's going to happen. So now, we get to assign them any value you want to. The book, and I also like it, let's assign those values 1. Okay? They're equal, let's assign them something. Okay? 1 is a nice, easy number to deal with. What would that make the hypotenuse have to be? Say again? Did you say 2? Okay. What's true about the two sides and the hypotenuse of a right triangle? Does the name Pythagoras ring a bell? Okay, and what does that tell you? Okay, if this is A, this is B, then this is C. So A squared, which is 1 squared, which is 1. Oh, he did decide to show up today. Pardon me?
I got stuck by a train.
Oh, okay. All right. If we assign 1 as the value for A, and B has to be the same because they're the same angle opposite, that's 1 squared is 1, plus 1 squared is 1, 1 plus 1 is 2, and C squared would be 2, so C would be, second? No, C squared is 2, so C would be, because we have 1 squared plus 1 squared is equal to C squared, right? Right? Okay, so this would be 1 plus 1 equals C squared. So that's equal to 2. So what would C be? How do you undo a square? Take a square root. So C would be the square root of 2. And you don't have to do a plus or minus because in trig, no side will ever have a negative link. No triangle ever has a negative link to the side. They're always positive. Now, they may be going in the negative direction. Yeah, that's okay. But this one, where this is 1, that's 1, that's going to be square root of 2. Now that we know that, and Jacori came in, where can we go from here? Can you tell me what sine of 45 degrees is? Perfect. 1 over the square root of 2, because the sine is always opposite over hypotenuse. 1 over root 2. Now, they sometimes don't like writing square root of 2 in the denominator or any square root in the denominator, so what's another way to express that? Say again? Okay. You can multiply both numerator and denominator by root 2, right? You have to do the same because root 2 over root 2 is 1. You can multiply by 1 anytime you want to. So this would be square root of 2 in the numerator. What would be in the denominator? 2. That is it. Square root of 2 over 2. Now, how about cosine of 45 degrees? That's the same thing. Okay, 1 over root 2, which is also square root of 2 over 2. And what would be the tangent of 45 degrees? 1 over 1, which is 1. Okay, there we have it. If you go back and check your unit circle activities, same answers, because the same. It's trig is trig is trig. It doesn't change whether you do square roots or whatever. I mean, whether you do unit circles or right triangles. Okay. Now, just for the funsies, let's do, and this is actually your checkpoint, what would be cotangent of 45 degrees? Say again? Of tangent, which is 1. Okay, that would be 1. And here we have David. All right. So we're only missing Austin, who's trying to do it remotely, and Ian, who doesn't make it in. Okay? So, how about secant of 45 degrees? What would that be? Secant of 45 degrees. Square root of 2 is the reciprocal of cosine. And that would just be, use this one, not that one. That would just be root 2. Now what would be cosecant of 45 degrees? Square root of 2 as well. It's reciprocal of sine. So just flip that, and you get root 2 over 1, which is root 2. You don't have to do that. You can just go by the formula too. All right. Any questions on those? We just did the checkpoints. Okay. If I went through those too fast or it didn't make any sense, then by all means go to larsonprecalculus.com and you'll hear them talk about it as well. All right. Can I erase what's here? Okay. Let's do example 3 before we get to the next slide. Now, says use the equilateral triangle shown in the figure off to the left here to find the values of sine of 60, cosine 60, sine 30, and cosine 30. So I'm going to try to draw an equilateral triangle. I'm not very good at this, as you have already noted. Okay? Let's just imagine that's an equilateral triangle. Now, what does equilateral mean? Second, all the sides are equal. The lateral sides are equal. So this side is equal to this side is equal to that side. Okay? Now, do you see a right triangle in there anywhere? No. Okay, there's not one. Because if these are equal sides, that means these are also equal angles. Okay? And what would those angles be? Say again? Not 45. Because 45 plus 45 plus 45 would be 135, and that's not 180. The three angles of a triangle always had to be 180 degrees. So, yeah, they will be 60. Because they're all equal, 60, 60, I can't write, and 60. Now mine doesn't look like they're quite equal, but let's just imagine, pretend they are. Okay. Now, I still don't see a right angle to use, okay? But what might we do? Drop a perpendicular there from that middle. And since those are equal, this divides this into 30 degrees on this side and 30 degrees on that side, because that perpendicular exactly bisects that angle, and if it exactly bisects the angle, it also exactly bisects the line down here. Okay? Now, we do have right triangles here. Either one you want to use. I think they use the one on the right. It really doesn't matter. But this one on the right is a 30, 60, 90 triangle. The one on the left is a 30, 60, 90 triangle. So we've got two. Either one you can use, they're fine. Now, at this point, note that, and I think I already said it, this perpendicular line exactly bisects the base, which means whatever is over here is also there. Now, at this point, that's the shortest side of that triangle, right? So what value do you think you might want to choose it to be? 1. Why don't we choose 1? Okay? So this will be 1. Now, if that's 1, this is also 1, which means that base was, yes.
Shortest side of the triangle.
Yeah. Yeah, just because it's the easiest number to deal with. Okay, it's nothing special. You can make it 3/5 if you wanted to. You can make it 714. I mean, 1's just a lot easier number for me to work. And I'm lazy. If you haven't picked that up yet, I'm pretty lazy. So I always go with the easiest way I can do it. Okay. So if this is 1 and that is also 1, what was that original base? 2. What does that mean these sides were? 2 also. So here we know this side. 2 here and 2 here. Okay? Now, depends on which side of this you're going to use. The book is using this side. So, this is now your right angle. That is now your hypotenuse. This is your short side. What's that side got to be? Any way to determine it? Pythagorean theorem again. And that says that a squared plus b squared, that's the one we're looking for, is equal to c squared, right? So a squared is 1 plus b squared, we don't know yet, is equal to what's c squared? 4. Okay? How could you solve for b squared? Pretty easy. Subtract 1 from both sides, so you get b squared is equal to 3. Okay, so what would b have to be? The square root of 3. And you don't have to do plus or minus, because none of our sides of a triangle is going to be negative. Okay, later we'll have them going in the negative direction, but the length is still positive. Okay. So there's b is equal to root 3. Okay? Now, we can do what they ask us to do, and that was find the sine of 60 degrees, the cosine of 60 degrees, the sine of 30 degrees, and the cosine of 30 degrees. Okay, how would we find the sine of 60? Perfect. Square root of 3 over 2. The opposite over hypotenuse. And you don't have to do a thing to rationalize, that's already in great form. What would be the cosine of 60 degrees? Second, 1 over 2. Perfect. Okay. How about the sine of 30 degrees? Second? Don't think so. We're not doing tangent. Okay, you thought we were doing tangent, didn't you? The tangent of 60 degrees would be the square root of 3, because you divide those and yeah. Okay. Right answer, wrong question. Okay, no, okay, whatever. Okay. what sine of 30 degrees? Go up to this angle. There's your 30-degree angle. And what is it? 1/2. Perfect. And what's the cosine of 30 degrees? Square root of 3 over 2. Since you did tangent of 60, you want to do tangent of 30? You don't have to. Say again? What? I couldn't hear. No. It's sine over cosine.
Oh, 1/2.
No. 1/2 over root 3 over 2 be 1 over root 3. Which, if you don't like radicals in the denominator, what would that be? Say again? Square root of 3 over 3. Okay. Now, since we went that far, we could go on and do the cotangent of 60. What would that be? Square, not just the square root of 3, 1 over the square root of 3, which is square root of 3 over 3. Okay? Adjacent over adjacent. Right. This is Did we do it wrong?
What you saying 60? What you said 60 though? That's right.
Yeah. Say that again. Oh, right, yeah. I'm sorry. What we're doing, since you started it by telling me to square root of 3, so it's your fault. So don't blame me for it, okay? Okay. We're just doing them because they're easy to do. Let's see. Cotangent of 60, that would be adjacent over opposite. So it would be 1 over root 3. And did you want to go on and do secant of 60? What would that be? 2. And cosecant of 60? Yeah, hypotenuse over opposite, which would be 2 over square root of 3. If you don't like the square root of 3 down there, what would that become? 2 root 3 over 3. Perfect. And since you went this far, and she made us do it before, we're going to have to do it again. What is cotangent of 30? Say again? Square root of 3. Perfect. And the secant of 30? Two over root 3, which you could also write as over 3. Perfect. And the cosecant of 30 degrees, which would be 2. Perfect. Way more than they asked for, but guess what? There's no extra charge. Okay? So you get those for free. Any questions on those? You see how you got them? Any questions? Those basic relationships that we did, which also stem from the reciprocal relationships, the ratio or quotient relationships, they all fit together so nicely, tie together like a bundle of worms, so that's not very pretty, is it? Okay. Any questions? All right, to move on. All right. These are example 1. Here we go. In example 1, you are given the lengths of two sides of a right triangle, but not the angle theta. Okay? Often you'll be asked to find the trigonometric functions of a given acute angle theta. To do this, construct a right triangle having theta as one of its angles, and then go to town with that. Okay? Now, that's all well and good, but now we're going back to doing what we just did. Sines, cosines, and tangents of our favorite special angles. Of course, the first angle is 0, and that's not very interesting, so we're not going to do it here. But the other angles are 30, 45, which example 2 did, 30, example 3 did, and 60, example 3 did. So we'll do these 3. Now, of course, 30 degrees is what in radians? Anyone remember? 30 degrees is how many radians? No, 1 radian is around 60 some degrees. So 30 degrees is how many radians? That's what the sine of 30 is, 1/2. What is the radian measurement for 30 degrees? Covering it here, and it's right there too, and right there too. 30 degrees is pi 6. Remember? Pi 6, pi 30, that's 30 degrees. Remember? Okay? Now, in the sine of 30 degrees, which is the same as sine pi 6, so they're measuring the same angle there, that's always 1/2. Now, here's, it's still up there. Yeah. Here's how I remember, get rid of some of the other mess that's in the way. Okay. A 30, 60, 90 triangle, the short side is always 1/2 of the hypotenuse. Or, hypotenuse is always twice the short side, and then the other side is always 3 times the short side. Okay? So, with that in mind, that's just my easy way of remembering this. The short side of a 30, 60, 90 triangle is the side opposite the 30 degrees, or pi 6, if you're in radians, is 1/2. Always. No matter if this was a huge triangle, a small triangle, whatever, the short side is always half the hypotenuse. So the ratio is 1/2. Okay? And then the other side is √3 times the short side. Okay. So that's what makes this 1/2. Now, the cosine of 30 degrees or pi 6 would be √3/2. That's that longer side over the hypotenuse. That ratio is always √3/2. The tangent is the opposite over adjacent, which is actually comes up being the sine over cosine. So when you put those there, that'd be 1/√3, because the 2's will cancel out here, and that would be √3/3. Okay? Done. 45 degrees, which we did in the previous example, the sine is √2/2. That one I remember, the two opposite sides, the two sides are the same, they're 1 and 1, that makes the hypotenuse √2. Pretty easy to remember. And cosine of 45 is the same as sine of 45 because the opposites and adjacents are the same. So that's √2/2, and then the ratio of those two is 1, so the tangent is 1. When you move to 60 degrees, now you have the sine of 60 would be that the opposite side is √3, the hypotenuse is 2, that's √3/2, which happens to be exactly what the cosine of 30 is. We're going to hit that a little bit later, but make that observation now. Okay? And cosine of 60 is going to be the adjacent side over the hypotenuse, which is 1/2. Okay? Which is exactly what the sine of 30 is. Okay? And then you can't do much with this. The tangent then of 60 degrees would be this over that, which is root 2's go out, and that's just root 3. Any questions on that? If we had done cotangent, you would have seen that cotangent and tangent are the same. Cotangent of 30 is the same as tangent of 60, and cotangent of 60 is the same as tangent of 30. You'll see why that's true a little bit later. Now the 45s, they are complementary angles with each other, so therefore sine and cosine are the same, and tangent and cotangent are the same, and secant and cosecant are the same, because all of them are relating to the same values. Now, in that box, note that the sine of 30 degrees is 1/2, and that's also the cosine of 60. That's what I just pointed out to you. That occurs because 30 degrees and 60 degrees are what kind of angles? Complementary angles. They complete each other. They add to be 90. Okay? Now, if you think about it, this is sine, this is cosine, are complementary of the sine. The sine of an angle is equal to the complementary sine of this complementary angle, the cosine of that complementary angle. Okay? And they are the same value. And that's what I pointed out to be true for secant and cosecant, tangent and cosecant, they typically are. Always are. In general, it can be shown from the right triangle definitions that cofunctions, that's sine and cosine, tangent and cotangent, secant and cosecant, cofunctions of complementary angles are equal. So the cofunctions of complementary angles, sine, cosine, tangent, cotangent, secant, cosecant, those are, if they're complementary angles that you're doing, they're going to be equal. That is, if theta is an acute angle, then the following relationships are true. What does it mean to be a complementary angle? They add to be 90. Okay? So sine of the complement of theta, 90 minus theta, that's going to be the complement of theta, is equal to cosine of theta. The cofunction of a complementary angle is the same as the function of the angle, and vice versa. Here's the one that says that. Cofunction of complementary angle is the function of that angle. Okay? Tangent of 90 minus theta is the cotangent of theta. Cotangent of the complementary angle is the tangent of theta. Secant of the complementary angle is cosecant of that angle, and the cosecant of the complementary angle is the secant of that angle. So all those go back and forth. This doesn't have to be our favorites. The 30, 60, 90, any. 12 and 78. Don't those have to be 90? That would be true of this. The sine of 78 would equal the cosine of 12. The cosine of 78 would be the sine of 12. And every one of them like that. Any two angles that are complementary, their cofunctions are equal of the complementary angles. Okay. Rather bizarre, but true. Let's see. I think they just skipped example 4. Okay? And this to me, okay, is a little bizarre. Okay? And here's what I'm going to, why I say it's a little bizarre. If you go back to 4.2 homework exercises, they had in there 47 through 50 was converting back and forth from decimal to degree form, but there wasn't a single example of that anywhere in 4.3. No, that was in 4.1. Okay, so here in 4.3, they're doing this. Okay, yet they gave you a homework exercise in 4.1 that we're doing. I thought, what's going on here? Okay. Actually, they're doing a little more than that. So here's what we're going to do with example 4. Okay? Use a calculator to evaluate the secant of 5 degrees, 40 minutes, and 12 seconds. You don't know that on top of your head? No, I don't either. Okay. How would you go about doing that? And it says using a calculator, but you can use pencil and paper or pen and paper ahead of time to set it up. So, do any of your calculators have a secret key on them? I'm guessing no. Most calculators do not. Now, some of the really big, expensive calculators have ways you can get to it, like modes or various things like that. But most calculators don't have that. So, you can do this either way. The book does it one way. I'm going to do it another way. Here's what I'm going to do. I'm going to say secant is 1 over what? You remember that? It's called the reciprocal identity. Secant is reciprocal to, not cosecant. It's the, okay. They're co-functions with each other, but they're not reciprocal functions with each other. Secant is reciprocal to what? Remember how we used to do when we were doing it? We used to do sine, cosine, tangent, cotangent, secant, and cosecant. Right? These two are reciprocal of each other. Cosine. So this is 1 over the cosine of, I like to put it in parentheses, 5 degrees, 40 minutes, and 12 seconds. Okay. Now, any of you have degrees, minutes, and seconds on your calculator? I kind of doubt it. You're in degree mode, not degree, minute, and second mode. Okay? So what we've got to do is get that into degrees. And what you do with that is get it into decimal degrees. And this is where they start their problem. You could have started it here or not, but 5 degrees is 5 degrees, okay? 40 minutes is 40 out of, how many minutes make a whole degree? 60 is 40/60th of a degree, right? Plus 12 seconds is what part of a minute? That's 12/60th of a minute, which would then be 12 divided by 60 again, and that would be 12 over 36 hundredths of a degree. So this is how you get them all to degrees. Okay. 5 plus 40/60th, they should be degrees down here too. No, I'm sorry, 40/60th of a degree, because this is minutes over minutes. This is seconds over seconds divided by minutes. Yeah. Keep it going. But all these give you degrees. Okay. That to me is just making it more complicated. So let me take those off. Not that. Okay. So this would be degrees. So this is how you do. So since you got this thing here is equal to this, you can put that instead here. So you can either do this with the reciprocal key or just do 1 divided. 1 divided by cosine, and when you open that parenthesis, put 5 plus 40 over 60 plus 12 over 3600. Close your parentheses. Oh, what mode do you make sure you're in? Degree mode. If you're in radian mode, it's going to give you a wacko answer. But if you're in degree mode, then do 1 over cosine of 5 plus 40 over 60 plus 12 over 360, 3600, I'm sorry. Close your parentheses, get equal. See if you don't. You don't have to do it this way, but this is how I do it. 1 divided by cosine, and that's automatically going to open up for you. 5 plus 40 over 60 plus 12 over 3600, close parentheses, equal. If you're in degree mode, what do you get? Anybody? Be sure you're in degree mode before you start any of this. You get an answer? Say again? I can't hear. Sorry.
I don't know how to put my calculator in degree mode.
Oh, okay. Calculator. Yeah, you probably already do. But you can see, one minute, that doesn't seem to be the right one. So much different. Here we go. Degree radian grad. So shift the yellow shift that, and this you want one. You want a radian moving with the 2. We're not going to do anything red, but if you want to one. So anyone get an answer yet? Should be a number slightly bigger than 1. Yes. What's that again?
40 and 60.
40 over 60. Yeah. 5 plus 40 over 60 plus 12 over 36. Just like we did here. 5 plus 40 over 60 plus 12 over 36. What you get? 1.0494966. It should be 2049166, right?
I got
1.00 or 1.04? 494. What's that? Okay. You may be right. I think they did some rounding off before they did it. So I think I'll go with yours. Okay. I don't have a calculator here, so I can't check it. But that's, it sounds reasonable to me. Okay. Now they did it slightly differently. They opened the parentheses, did the cosine of this, close that parentheses, then do a 1 over x cubed or x in minus 1 cubed, you get that. So that works just as well. It's about the same number of piece rates, so whichever you prefer. Okay. Anyone else get a different answer? Everybody get a 1.00 something another? Okay. All right. So that's example 4. They had you do the inner part of this back before, didn't show you how. Now they show you how on doing a bigger thing. All right, now, anyone need this a little longer? So let's go to, already done that, trigonometric identities. It's been a long time since I've seen Saturday Night Live. Nowadays, I go to sleep before it comes on. So, and frankly, I don't think it's as good as it used to be anyway. Back in the heyday, it was pretty funny. Eddie Murray and some of those others, you just couldn't beat. But sometime along the way, my wife used to like watching some. When we were younger, we stayed up and did it some. But one time when they were really, I thought, really lousy, they had a guy on there, and maybe y'all like him, named John Lovett, okay? I never found him very funny, and his skit was always the same. It was something about, it's sort of like a Rodney Dangerfield, but y'all probably don't know who he is. You know, how everybody mistreats him and stuff. Well, John Lovett did that same sort of thing with, get to know me, you know. He would whine on about various things and just scream out, get to know me, you know. I thought it was a really lame skit, okay? But he did it just about every week, it seemed like. It was way too often. But when you get to trigonometric identities, here's what I say. Get to know them, okay? You really need to get to know them because they're going to be your friends. Now, you probably think that's just as lame as I thought John, whatever his name, Lovett was. But please, get to know these identities. Here's what they are. We hit them in right circular trig. Here they're the same. They're the same. Trig's the same whether you're in, unit circle trig or right triangle trig. They're the same. And here are the ones to remember. Well, remember them all. The sine is the reciprocal of the cosecant, which means the cosecant is reciprocal of the sine. Those are called reciprocal identities. And similarly, the cosine is reciprocal of secant, secant is reciprocal of cosine, tangent is reciprocal of cotangent, and cotangent is reciprocal of tangent. Now, one set of these, the cofunctions, are also reciprocal functions. That's only tangent and cotangent. But sine and cosine, and secant and cosecant, are cofunctions of each other, but not reciprocals. The sine is reciprocal of cosecant, cosine is reciprocal of secant. Those are the reciprocal identities because they're one over each other. The quotient, and I've also seen texts that use ratio identities. The big ones are tangent is sine over cosine. I've already been using that, and cotangent is cosine over sine. The reciprocal of that, okay? So, those are your two quotient identities. And then comes your Pythagorean identities. Now, perhaps, I think you have already picked up on this. In your right triangle trig, what was sine? Opposite over hypotenuse. Remember, some old hag or whatever, okay? Well, what was cosecant? Cosecant was hypotenuse over opposite. See, they're reciprocals of each other, okay? So therefore the functions are reciprocal. And cosine was adjacent over hypotenuse, and secant was hypotenuse over adjacent. Reciprocals of each other. And that's why tangent and cotangent are both cofunctions and reciprocal of each other, because tangent is opposite over adjacent, and cotangent is adjacent over opposite. So those are reciprocal. Now, sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, divide those, multiply out the hypotenuse, and you get opposite over adjacent, which is exactly what tangent is. Okay, opposite over adjacent. Okay, taking oats away. So you see, they all work out this way. these identities build on each other. So let's do the Pythagorean identity. What is sine? Opposite over hypotenuse. And we're going to square it. Plus, and what's cosine? Oops, I didn't write it. Here it is. Adjacent over hypotenuse. We're going to square that. And let's see what we get. Well, what's, this would be opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared, right? What does that give us? Common denominator of hypotenuse squared, and this is opposite squared plus adjacent squared, right? And what's opposite squared plus adjacent squared? Okay, here's the opposite side, adjacent side, hypotenuse. That's an ugly triangle, but you know, just do it. Goodness gracious, that's the opposite. What's opposite squared plus adjacent squared? Pythagorean theorem. Say again. Opposite squared plus adjacent squared. That's the hypotenuse squared. And hypotenuse squared over hypotenuse squared is 1. There is your fundamental Pythagorean identity. Know it. Get to know it. Really useful. Many places. Sine squared of an angle plus cosine squared of the angle is always, always, always equal to 1. Whether that angle is a tiny angle, a big angle, it doesn't matter. Sine squared plus cosine squared is always equal to 1. Okay? Now, I'm going to erase all my scratch here, if that's okay, or do y'all need it any longer? Okay? So let me erase it. Now, I'm going to do something here. I'm going to start with that. Sine squared theta plus cosine squared theta, it doesn't matter what you call the angle either, is equal to 1. It's your fundamental Pythagorean identity. It comes from the Pythagorean triangle. Okay? Okay? Pythagorean theorem. Okay? Now, the first thing I'm going to do is divide everything on both sides by cosine squared theta. Now, of course, that won't work if theta is a half pi, any half pi, because that would be 0. So as long as it's not that, this works for any angle. Okay, this one, I do that. Now, what is sine squared over cosine squared? Sine over cosine. Tangent squared theta. Plus, and what's cosine squared over cosine squared? Second? 1, exactly. And what's 1 over cosine squared? Second? Secant squared. And guess what? That's exactly what you got here. They just reverse these two. 1 plus tangent squared theta is secant squared theta. There's another Pythagorean identity came straight out of that one. The only difference is, of course, tangent and secant both are not defined at all of your half pi's. Well, that's because cosine is 0 there, so you can't have them there. Okay? So you don't have to memorize these. You can always derive them. Okay? Just know that first one. Okay? Now, I'm going to do something else. This time I'm going to divide by sine squared. Okay? What's sine squared over sine squared? 1 plus what's cosine squared over sine squared? Oops. Cotangent squared. And what's 1 over sine squared? Cosecant squared. And there you have this 1 plus cotangent squared. I don't know what that symbol is there. I think I put 2 equal signs. Oh, that didn't help any, did it? Okay. 1 plus cotangent squared is equal to cosecant squared. Okay. Now, later, you're going to do all sorts of things. We might rewrite this as sine squared theta is 1 minus cosine squared theta, or cosine squared is 1 minus sine squared. You'll use those. Once you do those, you can factor those. There's all sorts of things. You can rewrite this to be subtract 1 from both sides. You get tangent squared is secant squared minus 1, or cotangent squared is cosecant squared minus 1. You can even do weird things like this. Secant squared minus tangent squared is 1, and cosecant squared minus cotangent squared is 1. There's so many ways you can write these 3 identities, whatever helps you. Okay. Now, we're in the first half of chapter 4. We're going to do the second half of chapter 4. Then we're going to do chapter 5. Chapter 5, you're going to be using all these identities out of your ears. So that's why I say get to know them. They're very, very useful. Okay? Any question on those identities? Now, they do make a little note here. Let's see if they do it here. Yes. I like to write it, and the book likes to write it too. It's pretty standard. What sine squared theta means is the sine of theta squared. Okay? Not theta squared, but the whole function squared. So I like to put it by the function itself. It's not doing anything to theta, it's squaring the function, sine of theta squared. Cosine squared theta is the same as cosine theta squared. Neither one of these are anything to do with sine of theta squared. You know, as if you didn't have a parenthesis here, sine of theta squared. That's sort of a ridiculous statement, and so is this one. So sine squared theta means that. You square the sine of theta. Okay. I think we may be ready for example 5. Yes, we are. So let theta be an acute angle such that sine of theta is equal to 0.6. There's where we're starting from. Theta is an acute angle, and the sine of that angle is 0.6. Find the values of cosine theta. How are we going to do that? What identity relates sines and cosines? Say again? What identity relates sines and cosines? The Pythagorean identity. You're absolutely right. None of these relate sines and cosines. This doesn't relate sines and cosines unless you happen to know tangent. But this is a relationship between sines and cosines, right? So we're going to use that one. Okay? So, let's use that identity. Sine squared theta plus cosine squared theta is equal to what? Always. Okay, we know what sine theta is. 0.6. So 0.6 squared is 0.36. Okay, plus cosine theta is what we're looking for. Cosine squared theta is equal to 1. How do we solve for cosine? Or at first, cosine squared. Say that one more time. Yeah, subtract 0.36 from 1.00, right? Okay, this goes away, and you get cosine squared theta is equal to what? 0.64. Okay? Now, what I want to know is what cosine theta is, not what cosine squared is. So how do I undo a square? Take a square root. So cosine theta is equal to what? 0.8. Perfect, perfect, perfect. Okay? You got that from your Pythagorean identities. And a little bit of work, but not too much. Okay, the B part says what's tangent of theta. Now, do we know anything that relates tangent to either sine or cosine or both? You got it. Sine theta over cosine theta, which would be sine theta was 0.6 divided by 0.8. And let's move the decimal one place to the right on both of them. That's 6 over 8. And any common factors between 6 and 8? 2. So that would be 3 over 4, which is 0.75. Now we've got tangent. These identities help you big time. Don't want to say you can get anything out of anything, but you can get a lot of value out of just this one piece of information. Sine theta equal 0.6, and all those identities, you can really go to town on those. All right. Any questions? Is it making sense? Okay? Now, let's see how they did it. I think it's pretty similar to what we did. To find the value of cosine, find an identity that relates what you know with what you're looking for. The only thing that relates sines and cosines is that Pythagorean identity here, which I told you before you're going to use a lot, in lots and lots of cases. So let's plug in what we know. Sine squared is 0.6 squared. And cosine is what we're looking for, and the sum of those is equal to 1. So that becomes, why in the world don't they go and square that? I don't know, but cosine squared theta is equal to 1 minus 0.06 squared, which is and cosine squared theta would be 0.64. Goodness, my throat's getting strange. Okay, then what is the square root of 0.64? 0.8. Okay. Do it on your calculator, you'll see it. If you know how to take square roots of decimals, you can do it directly. Okay. So, once you know that, you know sine now of theta, they gave it to us. Cosine of theta, we calculated it. Tangent theta, the ratio identity, or also called the quotient identity, sine over cosine, and that would be 0.6 over 0.8, which is 0.75. However you choose to get there, okay? All right. Now, all right, okay. I think I like to do what they just done here, using those definitions and the triangle shown here to check the results. Okay, you said the sine of theta was 0.6, so put that 0.6 over 1, and then you can do 1 squared minus the square, and your cosine, you got to be 0.8, so that's 0.8 over 1. And then do your tangent once you go to 0.8, which is exactly what we did here. You get 0.75. Now, you wanted to do one other thing. And this isn't a bad thing to do, but it's not necessary. Make this 1.0. Okay? That's okay, right? All those are to the nearest tenth. Now, multiply all three of those by 10. You're not changing the triangle, you're just expanding it. But it's the same relationship, same angle theta. So this would be 8, this would be 6, and this would be 10. Okay? If you multiplied each of those by 10. Okay? Now, common factor here was 2. Everything has a 2 in it, so let's divide by 2, divide by 2, divide by 2, and this gives you a 3, 4, 5 triangle, which we knew to be a Pythagorean triple. We hit that in the earlier section. Anything you can get to be a 3, 4, 5 triangle, or anything close to that, you're going to know a lot about it. So this sort of verifies what we just did was right. Okay? You didn't have to do that. They chose to do it. All right. I hear rumblings, or we get short of time? How much? 3 minutes. All right. Let's see. That was example 5. Let's see what we can do on 6. Okay. Nothing. They don't have 6 in here. So we're going to start next time with example 6, which means I'll wipe out that there. Okay. And let me give you some homework exercises. I know you don't want to leave home without those. Okay. In 4.3, you can do any of the odds 5 through 9. They're all at Calc Chat. 5's at Calc View. You can do either 11 or 13, both at Calc Chat. You can do any of the odds 15 to 21. They're all at Calc Chat. You can do any of the odds 23 to 27. They're all at Calc Chat. 25's at Calc View. You can do any of the odds 29 to 35. They're all at Calc Chat. Any of the odds 37 to 41, they're all at Calc Chat. 39's at Calc View. You can do any of the odds 43 to 51, they're all at Calc Chat. Did I say 43 to 51? 47's at Calc View. I think you can do all of 53 to 57. They're all at Calc Chat. Okay. I think the rest of them we'll pick up next time. All right. You may be able to go further. All right, good deal. Any questions? What we've done so far. Today, I think we started in 4.3, so I didn't make very much progress, did I? But there was a lot of kind of new stuff here. So we'll go on and end this.